so I hope you all found your exams. And the keys are right here. So you either had a version that had a little, had stats with lowercase letters or stats with all capital. And then you can find your version. So for example, if you have this version, and first of all, if you have a 0 right here, that's good. That means you circled your section. This is the number of points we took off. And this is the only one that people asked me to go over. And people did really well on this, by the way. So I was extremely pleased, really surprised too. So for this one, the correlation, if you include that little dot, you see how it makes it stronger? It gives it a positive correlation, whereas otherwise it would have been close to 0. Including it here lowers the correlation because it's way off the line. If you didn't have it, you'd have a pretty strong positive, but you include it, weakens it. Same here, same reasoning for all 3 of these. Including it lowers it. Look how far off it is from that. That little point is very far off from the regression line. All right, so let's go to the document camera. And if you have a question on your own exam, like if you think the points were added up incorrectly, if you think they're added up incorrectly or anything like that, you can come talk to me right after class, and I'll help you with that. Okay? Does that sound good? All right. What? Yeah, hi. You're supposed to be sitting down here. You can't see so well. What's your question? Okay, so you wanted me to go over question, which page? First page, question 2. Sure. Now, which version did you have? Did you have stat capitals? Yeah, with capitals? Okay, so you have this one. All right. Now, these are 2 perfect correlations. That means you can perfectly predict positively. So this would be temperature in Fahrenheit and Celsius. This is a perfect negative one, so that would be the number of points you got right or wrong on a 100-point exam. If you got 10 wrong, you'd know for sure you got 90 right. It's a negative correlation. Does that answer your questions? Now this one is how much you party and how much you drink. Positive correlation, but not perfect. And this one is miles per hour, miles per gallon, your gas mileage, and the weight of a car. Not a perfect correlation, negative, but does that answer? Okay. All right. Now, so I was really happy everybody did, not everybody, but people did very well on the average. I think it was a 90 average, which is really good for exam 2. Now, okay. So what we're going to do today first is we're going to finish off chapter 13. Where did we leave off? We left off looking at how when you just have 2 types of tickets in a box, for example, you can have lots of tickets, but just 2 different types. Like here you have 2 different types, etc. Then there's this really fast shortcut way to take the SD. That's where we left off. So now we're going to apply that to calculating the standard deviation of some of these roulette games. So for example, a gambler plays roulette 150 times, staking $1 on the number 10 each time. And I brought my roulette wheel here. Oh my goodness, look at this. What happened to the projector? You can barely see it. Oh, well, you can still tell, I guess. Remember how much? It's getting darker and darker, but you can see it. There are 38 numbers here, and if you bet on the number, oh, this little ball. If you bet on the number 10, there's only one way you can get a 10. Where is a 10? Right there. You can barely see it. Aww. And there's 37 ways you can't, right? So let's just start the box here. And a gambler plays, okay, he's betting on the number 10. So think about it, just make it for a single play. On one play, what can happen? You either win something or you lose a certain amount. That's all that can happen on a single play. You either win, if you win, and it's hard to win, but if it lands on that number 10, how much money do you win? Well, it tells you right here, it pays 35 to 1. So if you bet $1, that means you either lose your dollar, if it lands on any of the other numbers, or you win $35. So there's going to be 135. That would be so exciting. But all the others are going to be what? What else could happen? You can either win 35 or what else could happen? You lose. And what do you lose? $1. So let's write that as what? Negative $1. Now there's only one way to win. How many ways are there to lose? 37. There's 38 numbers altogether, so there's 37 ways to lose. Okay, now what's the question asked? What's the expected value? So if we played this game 150 times, what would we expect? First of all, would you expect to win or lose? You'd expect to lose because there's more ways to lose. In fact, check out the average of this box. If the average of the box is negative, that means you can expect to lose money. So let's see what the average of the box is. The average of the box is you have one ticket that's $35, and then you have 37 tickets that are all -1, and then we're going to divide by, there's 38 tickets altogether. So that's divided by 38. So we get -$2 over 38, which is, we can do it on our calculator here.
It's really dark.
I know, it's a dark day. It's dark in here. There's something wrong with this projector. We're going to have to hurry through this lecture before it dies. Can you see it well enough? No. You can't see that? Yes, you can. I can see it, and I'm much older than you guys. You're going to have to, how many people really can't see it? Raise your hands. And look where those people are located. Big surprise. Come on down. Come on down. There are seats. It's your choice. You can either be blind or you can be close to me. And you're probably going to choose blind. He's not going to be able to do anything. We've already dealt with, oh, my drink, my smoothie. Oh, who cares?
Power it off and power it back on. I don't think it will, but it did a little bit earlier.
Anyway, let's think about it. While he's doing that, let's think about it. So, I can't believe all of you would rather be blind than take a seat right up here. Like right here. Okay, it's better. A little better. We got to hurry before it loses power. Yay, Rich! That's Mr. Rich Furr. Give him a big hand. Okay, now, so this is about negative a nickel. Not going to do it on my calculator because I know it. So it's about negative a nickel. If you want to do it more exactly, we can do it to 4 decimal places. That's how the average of the box. So it says, what's the expected value if you play it 150 times? That's the expected value of the sum is n times the average of the box, which is 150 times negative a nickel. That means, and we get negative $7.89. Now, is it possible to get that? Is it possible to get negative a nickel on one play? Or is it possible to get any change at all? What do you think? You're betting you either lose that dollar or you get $35. So that's impossible, but the expected value doesn't have to be something possible. Like the average number of children is 2.2, but nobody has that. It's impossible. Now, standard error of the sum. Standard error of the sum is that square root law, square root of n times standard deviation of the box. So, square root of 150, whoa, standard deviation of the box. How do we do that? Well, are there just two types of tickets? Yes. So we say standard deviation of a box with just two types of tickets. What do we do? Remember, you take the absolute value of the difference of the tickets. Let's start there. So that's 35 minus negative 1. That's going to be 36 times. Times what? Times the square root of the fraction of the tickets that have one number on them times the fraction that have the other. Well, we have 38 tickets in the box, so that'll be our denominator. And what fraction of them have one of the tickets? It doesn't matter. 1. 1 out of 38 times 37 out of 38. And that part right here is 0.16. Okay, so when we do that, we get 36 times 0.16, and that is 5.76. So that is our standard deviation. So where do we want to put that? That's the standard deviation of the box. The box has a big standard deviation because look how far apart the numbers are. If that number was 1, we'd have a little standard deviation. Okay, but there's a big, you can get surprised. It's a big, if that was 1,000,000, you'd have an even bigger standard deviation. What's that sound? All right, so we just multiply this. This is square root of n times, it sounds like the ocean or something, doesn't it? I guess I just have that on. Hey, it stopped? No. All right, $70. This is our standard error of the sum. Each time we play, because it's driving me crazy. Does anybody have a clue what that is? Oh, it's a drill, and here I am thinking the ocean. In Illinois. Okay, so 70.58. So this means that you're likely to lose about $8, give or take about 70. Okay? Do you understand? You're likely to lose. That shouldn't be a surprise to you. So you're likely, if you'll keep playing, or if 150 different people played this, the house would be likely to lose. The house would be likely to gain about $8. You'd be likely to lose about $8, but there's a big variation because it's a risky game. Look at this. You could get lucky. It's very risky. It's going to have a big standard deviation. Whereas the games that just have one, on even money, it'll be 1 and -1, 1 and 1. It would have a much smaller standard deviation. Any questions on that? All right, let's do the next one. Now, all right, so this is another question, same type of thing, where it says a multiple choice test has 25 questions. Each question has 5 choices. So imagine one question. It has 5 choices, and we're going to be guessing. You have no idea which one's right. You're clueless on this exam. And you're just picking in. It's exactly like drawing from a box that has 5 choices, 5 tickets, only one of which is correct. And then you're just going to count up the number of correct answers. after 25 questions. So you're just going to have one that's correct, and what are the others going to be? You're not subtracting points if you get it wrong, you're just not getting any. So what are the rest? Zeros. So these are all zeros. Now, what would you expect? You can do this by common sense. The expected value of the sum after 25 questions, n is 25, you have a 1 out of 5 chance on each question, so 1/5 of 25 is 5. So you know that before you ever entered this class. But if you want to do it by the formulas that we were thinking of, you don't really need a formula here, but I gave you one. The expected value of the sum is n times the average of the box. And n is what? 25. And the average of this box is 1/5. 1 plus 4 zeros over 5. So that's 1/5. So just as you would have, if you were using common sense, you would have gotten the same thing. 1/5 of the time, you'd expect to get it right. But it's a chance process. So give or take about what? How likely would it be to get them all right? Well, that would be really weird if you got all 25 ones. But what is the typical error from 5? Give or take about what, typically? And that's the standard error of the sum, which, if you recall, depends on two things. The variation in the box, the standard deviation of the box, the bigger that is, like if that was a 5 or a 10, there'd be more variation. If that's more spread out, then of course, you don't know what's going to happen. There's more standard error in the sum, more variability. Times, each time you play, you introduce some error. When you're adding them up, you add up bits of error, but it scales as the square root of n, not as n. Okay, so we have that. So that's going to be the square root of 25. Oops, standard deviation of the box. Now you might think, whoa, that's really hard to do. But it just has 2 tickets. So we're going to subtract the absolute value of 1 minus 0. That's just 1, times the square root of the fraction. There's 5 tickets total. So 1/5 times what? Times what? 4/5. And that, you know what, you can do this in your head if you think of these as decimals. Another way to write that would be what? This part. Well, this is just 1, and this part is what? The square root of, what's 1/5? 2/10, right? 0.2. Isn't 1/5 0.2? 20%? Times 80% or times 0.8? Remember, they're always going to add to 1 even though we're multiplying here. So that would be the square root of 0.16, and we can do this in our head. What's the square root of 16? 4. So what do you think the square root of 0.16 is? 0.4. So there's our answer. Okay? By the way, the standard deviation of a 0-1 box, the biggest it can be, is if you have a 50-50 split. Think about it. If you have 0.5 times 0.5, you'd have 0.25. That's the biggest it can ever be. It will always be smaller or equal to that. All right, so this is the square root of 25 times well, I'm doing it out again, I'm sorry. I'll say 0.2 times 0.8, and that's, excuse me, that's 5 times, what's this? 0.4, which is what? 2. So you'd expect to get right, this is not a good score, you'd expect to get 5 correct, terrible, plus or minus what? About 2. So that's between what and what? That's between about 5 minus 2, about 3 right. Ooh, that's not very good. So that's between 3 to what? 7, correct, not very good. All right, so this is just the summary, and now it's time to do what? Move on to another chapter. Read the summary. Now, what we're going to do in this chapter is we're going to look at the expected value and the standard error of two different statistics. So far, we've looked at the sum, but often we're interested in not the sum, but the average or the percentage of something. Like in a public opinion poll, if I asked, if we took a sample, like that's like a random sample from the entire population, we might be interested in the percent of people who were against the death penalty, let's say. So that would be a percent. We wouldn't be interested in the sum total of the people. Or I might be interested in the average weight of the population. I wouldn't be interested in the sum weight of our nation in pounds of all the people. No, I'd probably be interested in the average weight. So we want to look at how those two statistics, average and percent, vary in a chance process. So far, we've just done the sum. And it turns out it's really pretty simple. So let's look at this. In the last chapter, we looked at the expected value and the standard error of the sum of n draws from a box. We'd be interested in that in gambling games. We're interested in our net winnings or losses. But now we're going to look at the expected value and the standard error in the average. We're going to start with average, then do percent. The average of n draws from a box. Now, let's start with the expected value. The expected value of the average of n draws from a box is just equal to the average of the box. It's just really, really simple. And if you think about it, you'd see why. You don't need any formula at all. It's just common sense that you would expect the average of the draws to equal the average of the box. For example, you have this box right here. You have tickets. 1, 3, 4, 5, and 7. And the average of those tickets, you add them all up and divide by 5, and what do you get? 4. And if you drew from this box, and let's say you got a 1, threw it back. Let's say you got a 3, threw it back. Let's say you got a 7, let's say you got another 1, let's say you got a 5. And you do this over and over and over and over again. And you get zillions of numbers, and let's say you got 100 numbers, and then you divide it by 100. Wouldn't you expect, I mean, you're not going to get it, but wouldn't you expect 20 of these, 20 of those, 20 of those, 20 of those, and 20 of those, all equally likely? You'd expect, you expect the average of the box. Each one has an equal chance. So it's the same as expecting the average of the box. Why would you expect the average of your tickets to be any different than the average of the box? Even if they didn't have an equal chance, whatever is the average, on the average, you expect to get the average of the box. So in 100 draws, made at random with replacement, the average of the 100 draws is computed. Okay? So you pretend you took 100 tickets, and each time you replaced them, right? You'd have to, because the box would be empty after 5. So each time you replace them, what do you think the expected value of the average of the 100 draws is? It's no formula. It's just the expected value of the average is just going to be what? It's just going to be the same as the average of the box. There's nothing, which is 4. You don't have to learn any formula at all. Okay? Does that make sense to everybody? You wouldn't expect to get more 7s higher than the average. You wouldn't expect to get lower than the average. You'd expect to get the average. Okay, I mean, the highest the average could ever be would be 7. The lowest the average could ever be is 1, but you would expect the average of the box. Now, but you're not going to get the average every time, of course. You'd expect the average of the draws to be the same as the average of the box, but of course it's a chance process, so it's going to vary due to the luck of the draw. And the typical variation around this average is called the standard error. And here's what the standard error is. So far, we had the standard error of the sum, which looked just like this. It had the standard deviation of the box in the numerator, but we multiplied by the square root of n. Here we're dividing. So this is the formula for the standard error of the average. All right? Remember, this was the formula that we had last time. So why, for sum, it makes sense that each time you're adding things together, you expect a little chance variation. So you expect the chance variation to grow. But it doesn't grow as n, it grows as the square root of n. Remember? Because we talked about sometimes you're going to have positive error, sometimes you'll have negative error. You expect to get bigger error, but you're not going to get, some of the error will cancel itself out. So it grows as the square root of n. All right, now, if we knew this, we could derive this very easily. Watch. How do you take an average? You sum things up. To change from a sum to an average, you just divide by n. That's the way you always take an average. You sum things up and divide by n. So just divide both sides of this by n. Now, if we do that, this right here is the standard error for the average. We change, standard error of the sum, divide by n, and you get the standard error of the average. But can we simplify this? Sure. Why does it simplify to this? We just left out one step. Can you see why it simplifies to this? The standard error of the average is that. Can you see why it simplifies to this? What if you rewrite this as the square root of n times the square root of n? Let's do it. So we'll keep everything the same. And instead of writing n, like instead of, let's say this was 25, I could write it as the square root of 25 times the square root of 25, 5 times 5, right? So I can rewrite n as the square root of n times the square root of n. I'm only doing that so that I can cancel this, and now you see how you get that formula. So it's pretty easy to remember. When you take an average, you're going to divide by the square root of n. Think about it. Let's go back to the box. Let's say you drew from here 100 times. 100 times you drew from here. The very biggest average, let's say you got all sevens. So you have 100 sevens. What would be your average of the draws? 7. So it can't be any bigger. It has to, and it's going to get closer and closer. The biggest you could ever get. You expect to get 4. The biggest you could ever get is 3 away from it. It would be so unlikely. So the more draws you have, wouldn't it make sense? Like if you just drew once or twice, you could get 2 sevens. And then you would have this really weird average of 7. But if you drew hundreds and hundreds of times, don't you think you'd get really close to 4? Don't you? So that's why your error decreases. The more times you draw, the smaller your error for the average. Does that make sense to everybody? Does that make sense? I mean, you can't get any bigger than, the biggest you could get away is 3 in either direction, because your average is 4, right? Oh, okay, the expected value for the average is 4. All right, so let's do this one as an iClicker. Maybe you're not ready for your iClickers yet, are you? I'm just afraid that we're going to just lose. Let's do this one together. We'll do the next one as an iClicker, because we have to go through this quickly before this disappears from our screen. Okay, so you'd expect the expected value of the average is what? We just for this. We have 5 tickets, and we know that the average of the box is what? 4. Can I just give you the standard deviation? Because you have to do it the long way. You'd have to subtract 4 from each one of these, get the deviations, square them, take their average and take their square root. So is it okay if I just tell you what it is? So that's 2. All right, so we'll do this one together first. So the expected value of the average is a no-brainer. No-brainer. Don't think, it's no formula. It's just the average of the box, which is 4. But this part is the standard, right? What you want to put in there is give or take what? That's the standard error of the average. And that is what? I'm just going to put the standard deviation on top. Now, do you think I'm going to multiply or divide by the square root of n? Divide. If I'd multiply, I'd get such a huge number. Divide by the square root of n. So I'm going to divide by 10. So I have 2 as my standard deviation, and I'm dividing by 10. If I multiplied by 10, I'd get 20, which would be insane. So that is equal to 0.2. So you'd get, it makes sense, you drew from there 100 times, and you took the average. You would expect it to be really close to the average of the box, just give or take a little bit. If you got all 7s, the average of your box would be 7. You couldn't say 7, give or take. I mean, that's the furthest away you could get would be 3 from here. So you can't multiply by 10. All right. Now we can do the next one. Let's see what the next one is. Why don't we do this one as an iClicker? But let me just, first let's work out the average of the box. What's the average? 36 draws. 36, so that's your n. 36 draws are made at random with replacement from a box that has these 4 tickets. Here's your box. So what's the average of the box? You add all these up, which is 12, divided by 4, you get 3. And the standard deviation, I'm just going to tell you because we're running out of time, is also 3. Okay? Should we try this one first? The sum and then the average. So here you're going to compute the expected value of the sum. Why don't we do this one together? We're just going to do this one because we don't have much time. So the expected value of the sum. Now for the sum, it's going to be n times the average of the box. Right? You could get, the highest you could get would be 36 eighths, the lowest you could get would be 36 zeros, but we expect to get 36 times 3, which is 108. But you're not always going to get that, so give or take what? Well, here it's a sum. So just write standard deviation. Standard error, standard deviation. Okay? Now, am I going to multiply or divide? Doesn't this look like the same thing? The standard, it's like a standard deviation for a chance process, a standard error. So you know they're almost the same thing. Now, am I going to divide or multiply by the square root of n? It's for the sum. So what do you think? Sum grows, so what do you think? Multiply. As if it's easier for you to write it on this side, it doesn't make any difference which side you write it on. I'm just used to writing it that side. Multiply by the square root of n. So what do we get? Square root of 36 times 3, which is 6 times 3, which is 18. And that's what we put here. Now, how about for the average of the 36 draws? If you drew 36 times, and then you took the average of those 36 numbers, wouldn't it be similar to just taking the average of these 4 numbers? Wouldn't you expect to get a similar, So what do you think that's going to be? The expected value of the average, and give or take what? That will be the standard error of the average. So let's do that one as an iClicker, just because I want to give you points for being here. So let's go to the here, and I'm just going to do this one quickly as an eye clicker. So that is right here. All right, so where do I make this bigger? Is this where I do it? Yeah. Okay, so let's start it, and you're going to answer this one first. You'd expect the average of the 36 straws to be what? The average of the box is 3. So you'd expect the average of the 36 straws to be, it's not hard. Okay, does everybody have enough time? Oh, gosh. All right, so can we stop here? No. And you know, the janitors are on strike, the SEU, so I'm making they want me to leave a mess. They say, support the strike, leave a mess. I leave a mess anyway, so it's not any hard for me. Okay. All right, so we're going to stop it. All right. And now, let's see. It's going to be the average of the box, and I hope you got that. Yay for us. Okay. Now let's start it again, and we're going to do this one. Give or take what? Give or take what? Here's your standard deviation. Your only question is multiply or divide by square root of n. That's your only question that you should be thinking. And n is just the number of times you draw out of that box. All right, we all done here? Can I turn off? Look how nice and white it comes out on this, though, on the PowerPoint. I'm stopping. Yell if you have any objections. Okay? So now we're going to look at this, and it's 0.5. Yay! Why? 3 over the square root of 36. 3, 6. Great, you got this. Now, let's go back to the document camera, and let's finish up here. So we know this is so easy. This is just expected value of the average is what? Just the average of the box. You don't even have to think about it. Give or take what? And you said it was 0.5. Why? Because we said the standard error of the average is the SD, standard error, but you divide by this, because you're taking an average, you divide by the square root of n. I told you that's 3 over the square root of 36, so that's 3 over 6, 0.5. All right, you've got that. Now, what happens, I just want you to remember how often we have 0, 1 boxes, because so often we're counting things. We're saying, is it this or is it not? Like counting the number of, we're taking the same box, 0, 2, 2, 8, but now we're not interested in anything but how many 2s we get in 36 draws. Not the sum, but how many 2s in 36 draws. And give or take what? Right? So you really can, I think the simplest thing to do, I mean, if you just look at it, in 36 draws, you know you're going to get half 2s, because half the box is 2s. So you know it should be half of 36, which is 18. But let's say the problem is a little more difficult, and for the standard error, we have to change the box anyway. So it's good practice to just say, okay, we are counting. Whenever we count, whenever you count anything, you count by ones. 1, 2. If I was counting the number of girls in here, I'd say 1, 2. And if I came across a boy, I'd just count him as a zero, not count him. So you go 1. So you count by ones and zeros. So just remember that whenever counting anything, you're going to make a 1, 0 box. All right, so this box is only going to have ones and zeros. I don't care what you're counting. When you're counting, you go 1, 2, 3. You're counting by ones. So these, the 2's, are going to change to 1's. Whenever you get a 2, you're going to count it as a 1. And what's the 8 going to be? We're not going to count it, and neither are we going to count the 0. All right, so that's what our box looks like. Now, what's it asking for? What's the expected value and the standard error of the number? Note, the expected value of the number is the same as the sum. It's the same as the sum. Every time I get, you're just going to be counting them up. It's how many ones you get. So the expected value of the number is just the same thing as the expected value of the sum. It's just for a 0, 1 box, it would be the number. So it's what? What are you going to have? N times the average of the box is a very long way to get 18, which we could see just by looking at this, which is 36 times the average of the box. And of course, in a problem this easy, you could just say 18 if you could see. Half the time you're going to get, okay, 36 times the average of the box. Well, the average of the box is 1 plus 2 over 4, which is a half. So here's a roundabout way to get 18. And of course, you could just write down 18. If it was this easy a problem, you wouldn't have to show that. Now, but for the standard error, nobody can do that in their head, I don't think. Or just see it from here. You'd have to think, okay, standard error of the number is the same as standard error of the sum. Okay, it's the same. Do you want me to write that just so it looks symmetrical? Is the same as the standard error of the sum. It's just for zeros and ones. Okay, so now, just no standard error, standard deviation. Okay? That's what it is, but it's a chance process. We're summing things up. So do I multiply or divide by square root of n? Multiply. I'll just put it on this side for a change. Okay, so you multiply by the square root of n. So, what is that standard deviation of this box? Well, the standard deviation of the box is, you take the difference between the two types of numbers, so that's 1 minus 0. Of course, if you want to put the absolute, you know that it has to be positive, over the square root of, you have 4 tickets. Half 2 of the 4 have that number on it, times 2 of the 4 have that number on it. So really, this is just 1. You don't really have 1 times anything. And this part, you can put a 1 times, but you don't need it. I think it's easier to think of it as a decimal, as 0.5 times 0.5, which is equal to the square root of 0.25. Now, what do you think the square root of 25 is what? The square root of 25 is 5. So what do you think the square root of 0.25 is? It is 0.5. So that's what this is. That's the biggest standard deviation you can have in a 0, 1 box. So it's 0.5 times, what's the square root of n? The square root of what? You probably forgot what we're doing here. What's n? 36. So that's 0.5 times 6, which is 3. So you'd expect, this is all we're saying, 18 plus or minus 3. 1's from that box or 2's from those. All right, now we are going to look at, we did a 0, 1 box. You know what we're going to do now? Before you even turn the paper, let's think about it. Before you even turn the paper, what if this was a percent problem? Instead of saying the expected value for the number of 2s. What if I said the expected value for the percent of 2s in 36 draws? What percent of 2s do you expect to get in 30? And no matter how many draws, I don't care how many draws, what percent do you expect to get? 50% of the box is 2s, so what percent of your draws do you expect to be 2s? 100%? 50% I'm going to make you answer this rhetorical question. 50% of your box is 2s. So what percent, if you draw 36 times, what percent of your draws do you expect to be 2s? Say it louder. 50, right. And in this box, which is the same thing, what percent of the box do you expect to, if you drew from here 36 times with replacement, what percent, so you have 36 numbers you write down. Just want to make it really vivid. Oh, I got a 0. Oh, I got a 1. Oh, I got a 0. Oh, I got a 1. 1, 1, 0, 0, 0. I did that 36 times. What percentage of them do you expect to be 1s? 50% of the box is 1s, so what percentage of these draws do you expect to be 1s? 50%, right. Give or take what, though? That would be the standard error for percent. And it's just like an average. It's an average. It's exactly like an average. How do you get a percent? In this, you count up the number of 1s and divide by however many there are. 1, 2, 3, 4, 5, 6, 7, 8, 9. In this case, it would be 4/9. To change it to a percent, I just change the decimal to a percent. It's an average, right? So it's going to be the same. So let's do it. All right. So what we're doing here is the expected value of the percent and the standard error of the percent. Hey, are you bored? Is that why there's sort of rumblings? Are you really that bored? How can you be that bored? I actually think this stuff's interesting. How it all ties together. You know, you have just one formula. First, it's just the square root law. It's sort of remarkable. I think you'll feel that after a while when you see what we can do with it. But there's just one law. That's why you don't need any formulas for this course. In another course, you'd get bombarded with them. Bombarded with them. I'm just boiling it down to one formula for you, which is sort of astounding. You should be happy. It's just, it's astounding it's not always taught this way. That's what's astounding. But in any intro class, you're going to get lots of different formulas. Oh, use this when you for a percentage. Oh, use this when you have the, it'd be like a whole different ball game almost. You wouldn't even recognize the formula. You probably have seen it, the square root of p times 1 minus p over. All right, anyways. So, you just need to remember one thing for all these standard errors. And that's that you have a standard deviation of your box, and you either multiply or divide by the square root of n. Now, so what do we have so far? The expected value of the average of n draws is the average of the box. That's no-brainer. The expected value of the percent of 1s is just the percent of 1s in the box. Again, no-brainer. Now, what have we had so far? Standard error of the average. You divide by the square root of n. And you do the same exact thing for a percent because it's really just an average. This is an average right here. If I wanted to look at the percent in the class that were girls right now, I'd just count you up, count you all as 1s that are girls, and divide by however many people are in the class. And let's say it came out to be 0.6. To change that 0.60 to a percent, I'd multiply by 100. So that's all that is. All right, so let's just do this same problem again. And this time, we've already done this, but the problem says, finally, suppose you draw at random with replacement from the same box. But now you're interested in the percent of 2s, not the number, but the percent. So you want to take the percent. So you change again to a 0, 1 box. And the expected value of the percent of 2s, there's 50% 2s here, or 50% 1s here. So the expected value of the percent is just going to be equal to the percent in the box. The percent of 2's in that box, or the percent of 1's in here. So that's 50%. Now, what is the standard error of the percent? What do we do here? Well, the standard error of the percent, okay, so far I got this. Just tell me, multiply or divide by the square root of n? Divide. That's just going to give you a decimal. And to change it into a percent, what do you have to do? Multiply by 100. If I say multiply by 100%, it looks weird, but you know what I mean. Because it looks like, oh, that's just 1. No, I just multiply by 100, I'll say to change it, to change from decimal to percent. Okay, you got it? So let's do that. So what do we do? What should we do? Do we remember we're using this box here? So we're going to say equals, remember this, the SD of the box here, SD is equal to 0.5 of that box. We just did it. It's the square root of 0.5 times 0.5. Okay, so we have 0.5 divided by what? 36 times 100. Now you'll have the percent. And when you do that, you get 8.3%. So you'd expect 50% 2's plus or minus 8.3%. That's all we're talking about here. All right, we're almost done. All right, we are almost done. It's going to get really interesting when we use this stuff, believe me. We're just trying to get these basic laws down, and then when we use them, it's going to be really easy or fun. What? Yeah? Okay. I know. Just trying to see if I... Okay. All right, so this is what we have. Now, notice. Let's look at our laws next to each other, these square root laws for standard errors next to each other. Where are they? Hold on. Oh, well, let's go to this page. Okay, so this square root law leads to the law of averages. What does the law of averages say? This law of averages says what? That with more draws, the closer the average of the draw is likely to be to the true average of the box, even though the sum of the draws tends to drift further away. What do I mean by that? Like if you flip a coin, the percentage of heads will get closer and closer to 50% with the more draws. Am I likely to get, let's say I flip a coin just a few times, 4 times. And then I flip a fair coin 4 million times. Do you think I'm more likely to get close to 50% heads with 4 times or with 4 million times? 4 million times. I could easily get all tails with 4 times. But I'm not going to get all tails in 4 million times, am I? With a fair coin. So you're going to get closer. Your error is going to go down as a percentage. But what does it mean for the error to go up as a number or as a sum? Well, if I flip it if I flip it 4 times, you'd expect me to get 2 heads, right? Wouldn't you? If I flip it 4 times, how many heads would you expect me to get? Wake up. 2. Give her, and what's the biggest my error could be? What if I got all heads? What would be my error? 2. I can't even get more than, now let's say I flip it 4 million times. You'd expect 2 million heads. And my error can be a lot bigger than 2, can't it? Can't it? Isn't it usually going to be a lot bigger than 2? So your error goes up as a number, as a sum, but down percentage-wise, as an average or a percent. That's all this says. Okay? In the long run, you'd expect to happen what happens. All right, so let's look at this. So the more draws, the bigger the standard error for sums. Standard error for sum. You multiply, so it's going to get bigger with more draws. But standard error for average or percent, you divide. So it's going to get smaller by the square root of n. You might, So 100 times as many draws means, for the sum, it means the square root of 100, which is 10 times as much error. But as an average or a percent, it's going to be divided by the square root of n. So it will be 1 over the square root of 100, which is 1/10 as much error. Okay? That's basically that. Now, let's just do some problems then. All right. This is our last page, guys. Our very last page. And this dark screen is making you much less attentive, I think. Is that what's happening? Because you can barely see. It's like a sleepy screen. I'm really sorry. We'll get it fixed by next time, okay? But let's bear with it this time. I'm really sorry. I know, I can just tell this class is just not the same as usual. But we've just got to do this last problem, and then we'll be done. And next time we come here, it will be bright and pretty, all right? Okay? I apologize. It's probably hard for you guys. Okay, so let's just go through this last page, all right? Now, in tossing a fair coin, fill in the blank to make the chances equally likely. I just want you to think about this, all right? So if you toss a coin 4 times, you'd expect to get 2 heads. Let's just say 2 plus or minus 1 head, getting between 1 and 3 heads. The chances of that is about as likely as in 36 tosses, getting between what and what? 18 plus or minus what? How would you go about this? Well, you want to compare the numbers, 4 tosses versus 36. How do those numbers compare? 36 is how many times bigger? 36 divided by 4, it's 9 times bigger. 9 times bigger. So how does that change your error? How does it change your error? See, 9 times bigger, your expected value is just n times it's just 9 times bigger. But the error doesn't change. It doesn't scale as 9. It's going to scale as square root. But let's go through it. So we're counting or summing up the heads. So our error will be multiplied by what? Do you think by 9? So I should say plus or minus 9 here? No, it's the square root law. It's going to be multiplied by what? The square root of 9, which is 3. So what's going to get multiplied by 3? Instead of you'll have 1 head, you'll have 1 times 3 heads. The error will increase from 1 head to 3 heads, to 1 times 3, 3 heads. So that's what we should put in here. 3, which is what? Between what and what? 15 and what? 21. is the same as between 1 and 3. The chances of getting between 1 and 3 heads is the same as getting between 15 to 21 heads. Does that make sense now? All right, let's do the next one. Now, let's try this. 50% plus or minus 25% heads. What do I mean? Between 25% to 75% in 4 tosses. This is the same problem as a percentage problem. Do you see that? Isn't it? Between 1 and 3, 50, what I'm doing here is I'm saying, here it is as a sum. 2 out of 4, 50%. Between 1 and 3 out of 4 is between 25 to 75%. Now, you see how your expected value is still going to be, here the number changed because we're talking about a number. So we said 2 out of 4 is the same as 18 out of 36. But now we still expect to get 50% heads, but what's our percentage error? That's what we're talking about, okay? So compare the two numbers. We're doing exactly the same thing. It's 9 times more, but now we're looking at percent. So our error is going to go down, down. The more tosses, the lower your percentage error, the closer you'll get to 50%. So it's going to be divided by what? 3. I'm doing exactly the same thing. It's going to be divided by the square root of 9, divided by 3 instead of multiplied by 3. So what does that mean? Your error will decrease from what? 25% heads to 25 divided by 3, which is what? 8 1/3%. Does that make sense? So we'll put that here, 8 1/3%, which will bring us up to 58 1/3, and bring us down to 41 2/3, 41.67 to 58.33. That's what we'd expect. You'd expect it to zero in on 50%. It's not going to be between 25% and 75%. That's what you get with 4 tosses. You're zooming in closer to 50%. And if you tossed it even more times, you'd zoom in even closer to 50%. All right, now let's do this one. 10 plus or minus 2 in 20 tosses is about as likely as 1,000 plus or minus what? Well, we're just in the number, we want to compare those two numbers. How many times more are we tossing it? Well, compare 20, we're tossing it 100 times more. 2,000 divided by 20 is 100 times more. Times more tosses. Okay, 100 times more tosses. And you can see how the expected value is 100 times more. You'd expect 10 out of 20. And since if you toss it 100 times more, 10 times 100 is 1,000. So you'd expect 1,000 out of 2,000. That's pretty easy. But how about this part? This is not going to go up by 100. What do you think it's going to go up by just in your head? What do you think this number is going to be? Do you think it's going to go up to 200? I mean, do you think it's going to go up to, where am I looking? Right here. Do you think this is going to go up to 100 times more error? No, it's only going to be how much more times error? 10. So it's a sum, so we want to multiply. Whoa, and what do we want to multiply by? 100? No, square root of 100, which is what? 10. So we want to multiply what by 10? This error. So we want 2 will go up to 2 times 10. This right here. That, which is equal to 20. Does that make sense to you? That's the same thing. In other words, if we wanted to say, we'd say, if we wanted to write it like in parentheses, what would it be? Between what? 8 and 12. And here, what would it be? Between 1980 and what? Those two are the same chances. Getting between 8 and 12 heads and 20 is the same chance as getting, whoa, I did this wrong. Why didn't you yell at me? It shouldn't be this. It should be what? 980 and what? 1,020. I am so sorry. How can you get 2,020 heads out of 2,000 tosses? All right, sorry about that. And now, finally, our last one, this says 980, I'll just rewrite it, to 1,020. This interval is the same as this interval, the chance of getting it. All right, now lastly, 50% plus or minus 10% is the same as 50% plus or minus. First of all, is it going to go up or down? Just right. It's going to go down because we have percent. And it's going to go down, so you're going to divide. What are we going to divide by? The 10% by what? What are you going to put in here? The square root of something. And what are you going to put in here? It's 100 times difference, so it's going to be the square root of 100. So it's only going to be 1%. In other words, 40% to 60% in 20 tosses is equally likely to what? In 2,000 tosses. It's equally likely to what? And did I do that wrong? I did that right. It's equally likely to what? 49% to what? 51%. Does that make sense to everybody? Probably not right away, but it will take a while. Okay, see you next